The Best Way to Explain It, Episode 14. Podcast listeners to another episode of The Best Way to Explain It, the podcast that's almost as captivating as one of those cooking videos on Facebook that you watch when you're supposed to be paying attention in class.
Or when you're working and you don't really want to work.
And not working at all.
Yeah.
But, those... Every time I see them, I have to watch them completely all the way through to the very end till they take the bite of the food.
It's kind of like Bob Ross, though. Like, you have to play it in slow motion. Otherwise, you don't know all the colors he's painting with or all the ingredients that they're using. I don't know why, but it is satisfying to finish watching those videos.
It really is. And, I never turn the sound on. I just watch them and... enamored with recipes that I'll likely never make, so it's like I'm living vicariously through what they're making, and it's really good for me.
And you're like, all right, how many sticks of butter are in this one?
Oh yeah. It's like, well, sometimes you'll watch them all the way through, and then you'll realize, oh, you can do that with food. You can put those foods together. Oh, you can dip bacon in chocolate. Like, that's allowed.
Yeah. I always get like cocktail videos with different, strange cocktails. And they're like, oh yeah, use this $500 bottle of scotch and these bitters to transform this into a blueberry mouth surprise.
Okay, now we need to make a cocktail called the Blueberry Mouth Surprise.
Sounds good.
The official cocktail of The Best Way to Explain It.
I'm not going to use 500-year-old scotch for it, though. So
that would probably be even a bit too old.
Yeah, probably a little bit.
So, yeah.
All
right, so just a quick mention. We're going to, again, just plug our giveaway that we're doing. I just bought the Amazon Echo. It's awesome. I guess I don't know. I assume it is because I assume it works. But so if you guys remember, just to enter this giveaway for the Amazon Echo, you just got to leave a review and rating on iTunes. Screenshot your review/rating and send it to me at scott@thebestwaytoexplainit.com, and you will be entered to win an Amazon Echo free of charge.
Sounds pretty cool to me.
Yeah.
I think at this moment we only have one entry, so chances are still pretty high.
Yeah, you're probably going to win it if you enter, so there's really no reason not to. And you have until December 17th to do it, so... But, why wait? It takes 2 minutes to do.
Truth.
Maybe not even that much.
Yeah, I don't know, because if I rate the show, I'll probably, turn listeners off.
It comes off a little arrogant.
Yeah.
I like the show, personally.
I personally would give us 5 stars.
The same here.
Yeah.
Well, me 5 at least. You
2.5. All right, that's
easy.
That's a simple. That's just simple math,
Well, right, yeah.
we give ourselves stars based on how much work we put into this podcast.
Yeah, pretty much, right? Wait, but you're the one explaining something today, and you're actually going to be explaining a listener request, aren't you?
Oh, another one. Keeping them going. Actually, it's a pretty interesting request, and hopefully I do it justice. If not, I think I left enough room for me to come back to this subject later on after,
all right,
studying physics with Buddhist monks in the Himalayas. Yeah.
Next year.
Yeah. Yeah.
Yep.
So, as I mentioned, it's a physics topic, but more specifically, it was a suggestion sent in by Drew, and it's string theory, because you've probably heard of it. Well, I know you've heard of it, but you've probably heard it on Big Bang Theory, and like Sheldon's research was about it for quite a while, and then they like made some news happen where string theory wasn't the best way to go, which actually did happen in real life, didn't it? And I didn't look that up because
that was kind of back when the show was good.
yeah. Well, now if you rewatch those episodes, you're like, wow, I liked this.
Yeah. Canned laughter.
Yeah.
That's what this show needs, a laugh track.
Oh, no. Our jokes would be even worse if we added a laugh track. But, so string theory, the main reason we want to learn about it is because it breaks up a friends with benefits relationship for Leonard on that show.
Yeah.
But, I really think it works out in the end because he gets to marry Penny on the show.
True.
And he dated her for a little while in real life.
Yep.
Oh, man. All right. So let's dive into this.
Let's do it.
So I could just start out with this really simple one. We could make it the shortest podcast ever. And basically, I'll just tell everyone that all matter is made up of tiny strings, and that's what string theory is.
Huh.
But I have a feeling you want to know a little bit more than that, don't you?
It could be. That could be the case. I imagine Drew would like to know a little bit
more. Probably.
Mm.
But I guess that, like I said, it's not the best way to explain it. And in keeping with our namesake, I'll discuss it a little bit more. String theory proposes that the fundamental constituents of the universe are one-dimensional strings rather than point-like particles. So instead of the atoms that you probably learned about in high school, physics or chemistry, they are one-dimensional strings, very tiny, and what we perceive as particles are actually vibrations in loops of string, each with its own characteristic frequency. So each atom would be a string vibrating at a certain frequency, and then because we can't perceive these strings, they come off looking like particles.
Okay.
Yeah. So string theory originated as an attempt to describe the interactions of particles such as protons. It has since developed into something much more ambitious, an approach to the construction of a complete unified theory of all fundamental particles and forces. We'll get into what those are in a little bit. Previous attempts to unify physics have had trouble incorporating gravity with the three other forces, so string theory not only embraces gravity, but requires it. String theory also requires 6 or 7 extra dimensions, which is where it runs into some issues. But, when in doubt, just say everything's like 11 dimensional.
Yeah, right.
Which it would be hard to, it's still hard for me to grasp what that looks like,
Well, because we don't have any experience of it, right?
Yeah, exactly. The study of string theory has also led to the concept of supersymmetry, which would double the number of elementary particles. Again, we'll get to that. And practitioners are optimistic that string theory will eventually make predictions that can be experimentally tested. But for now, it's really theoretical and not easily experimented.
There's not much practicality right now with it. Okay.
Yep. Because we would need 7 extra dimensions.
And we don't have those.
And unfortunately, we can't just pretend there are extra dimensions right now. So let's break down some of those topics I hit on: the elementary particles and the 4 basic forces. Elementary particles are in classical physics include the proton, the neutron, and the electron. The proton is positively charged, the neutron has no charge. Protons and neutrons are in the nucleus of the atom, and then the electron is negatively charged and it floats around outside of the nucleus. These 3 particles form the atom and thus far are the smallest observable thing known to mankind. It's what everything's made of.
Yeah.
Yep. And then the 4 basic forces are gravitational, electromagnetic, strong, and weak forces. These 4 forces govern how objects or particles interact and how certain particles decay, according to Britannica.com. The gravitational force is the one that, sucks when you trip and fall and scrape. It was discovered by Isaac Newton, and I have a feeling everyone's kind of experienced gravity throughout their life.
Likely.
If you haven't, let us know, because that would be interesting.
That's awesome.
The electromagnetic force was given scientific definition by James Clerk Maxwell in the 19th century. This is the repulsion of alike and attraction of unlike electrical charges. It also explains the chemical behavior of matter and the properties of light. So when you were a kid and you would play with magnets and try and push the positive ends together, and to no avail, that was the electromagnetic force.
Okay.
Yeah.
So is that like... So magnets.
Yep.
Right.
Yep.
Okay.
Magnets, and then forces generated by electrical charges as well.
Okay.
Yeah.
Cool.
Yep. Meanwhile, the strong and weak forces were discovered by 20th century physicists when they finally probed into the core of the atom. So, the strong force acts between quarks, which are the constituents of all subatomic particles, including protons and neutrons. It holds the nucleus of an atom together despite the repulsion of positively charged protons. So the strong force is the strongest force known to man because it holds all those protons together.
Mm-hmm.
And then the weak force occurs in certain forms of radioactive decay and in the nuclear reactions that fuel the sun and other stars. Electrons are among the elementary subatomic particles that experience the weak force, but not the strong force.
Okay.
Yeah.
So I've got a quick question about this string theory. So you said it's so string theory is based, or it's named as such because it's the theory that all matter is composed of one-dimensional strings?
Yep.
So how can a string be one dimension? Isn't that just strings have two dimensions, right?
Realistically, the way we would think of them, they would have 3 dimensions.
Right.
Yeah.
I don't know. I just... String seems like an odd name
Yeah,
to call a one-dimensional object.
Really, that's just the way that they call them, or that they describe it. I don't know. How else would you describe, like, little lines, one-dimensional lines? And I don't know if one-dimensional is the best way to explain or to, like, call it, but that's what all of my research has described.
No, I think you're correct.
Yeah.
I just think it's,
Yeah.
poorly named.
Well, they say that these strings can be open or closed loops, which I think if you have a closed loop, you would have to have at least 2 dimensions, right?
Right.
But that's probably above my head at this point in my
fine.
understanding.
Yeah, just a comment.
Yeah. That's a good question. That's something I'll have to look into when I do go deeper. I would like to go a lot deeper than I go, but I wanted to get the basics out. This is
All right.
we should call it the basics of string theory.
Yeah, that's probably good.
Yeah. So as was touched on earlier, the reasoning behind string theory is to create a unified theory relating all 4 basic forces into one force. And string theory seeks to unify these forces with these tiny vibrating strings, replacing the 3 fundamental particles. Instead of the fundamental particles, the tiny vibrating strings that are too small to be observed by today's instrument correspond to each of the particles and determine the particle's mass and size. Really what this does is it breaks down having to separate all those forces, and it says, well, they're all strings, and they're all connected through these one-dimensional strings. Does that make sense?
So I just want to repeat back what I understand.
Yeah.
So right now, or what kind of is the conventional thinking, so you have these 4 forces that interact or act upon the 3 fundamental particles, right?
Yeah.
So that's the old way, and the string theory says, no, those fundamental particles aren't actually like different. They're all just strings. And so sometimes the gravitational force acts upon this string. Sometimes we get a weak force acting on it. But since they're all the same thing, or there's no like real distinction between them, like the force can be thought of as the same force.
Yeah, as
interacting with that string
as a unification of the forces. So
right.
we have, and I'll get to this in a little bit. We have so many similarities between certain otherwise unrelated subjects, such as magnetic or light waves, and then we have water waves, which are, you know, acted upon by gravity and stuff, whereas light waves are a completely separate entity. And I'll get to that in a little bit, but yeah, sure. What they're really trying to do with any sort of unified theory is trying to unify those four forces together, and they can't.
Gotcha.
They haven't been able to do that with gravity, and that's where other things have failed, and that's why string theory is such a popular theory among scientists. Okay. Yeah.
Oh, so is string theory the theory of everything? That's that.
They're trying to make it a theory of everything, and I'll get to that in a little bit too. Yeah.
Gotcha. Okay.
Yeah. So because Einstein and his discovery of the famous equation E equals mc squared, there is a relationship between an object's vibrational frequency and its mass. It's a central component to string theory. So however much something is vibrating, that's how much energy is within it. And then it's really difficult to grasp that without going through an entire course within like chemistry and physics. Basically, sure. Like you and I both have our own like vibrational frequency, and we're a very slow vibrating organism versus an atom or something, right. Because our mass is so large. So
okay. So the bigger our mass is, the less we vibrate.
Yep. Okay. And I had to do some calculations to figure out like the vibrational frequency of a horse. So yeah, it was really interesting. But yeah. So Einstein developed the theory of relativity, which opened up the universe to a multiple dimension sort of thing, to a multitude of dimensions.
A bunch of different dimensions.
Yeah. So relativity worked in 4 dimensions just as well as it worked in 40 dimensions. Unfortunately, string theory only works in 10 or 11 dimensions, as I joked about earlier. So if scientists can find evidence supporting string theory, they will have limited the number of dimensions that could exist within the universe. So let's say we perceive the world in 3 or 4, if you want to count time as a dimension. I do. So if we live in 4 dimensions.
Sure.
If we could nail it down to 10 or 11 and say string theory worked, then they could say, well, we can discover, 7 more dimensions out there, and that's another purpose behind string theory.
Okay, so we could have an upper limit.
Yeah.
Okay.
In order for these extra dimensions to exist, they must exist within a compact space. So if the space is really tiny on the scale of the strings that we're talking about at 10 to the negative 33 centimeters, that's a 1 with, I believe, 32 zeros in front of it before a decimal point. Yeah. Then we would be unable to detect those dimensions. So they may exist just at such a small level that we have no clue how to detect them at this point.
Okay, so is that it's not a impossibility to detect them, we just don't have the technology to do it right now?
Yeah.
Okay.
Yep. Oh, let's see here. So I learned a lot from an article called What Every Layperson Should Know About String Theory. It was on Forbes, and I tried to read through what the article that they pulled a lot of their information from, which was what every physicist should know about string theory. And I felt like I had stumbled upon some conspiracy theorist. Like it looked like the Zodiac Killer wrote another letter.
Did it feel like that Charlie Day picture where he's trying to explain
the mailroom episode of Always Sunny in Philadelphia? Yeah, but they have a really interesting little paragraph here. It's about a theory similar to string theory and kind of the extra stuff that they had to pull in to help make string theory work, or in this case, quantum field theory. So they said the way the quantum field theory works is that you take a particle and you perform a mathematical sum over histories, and you can't just calculate where the particle was and where it is and how it got to be there, since there's an inherent fundamental quantum uncertainty to nature. That was fun to say. Instead, you add up all the possible ways it could have arrived at its present state, appropriately weighted probabilistically, and that's how you calculate the state of a single particle. So that's how we calculate what a particle is, where it is, and what state it's in.
Sure.
And because Einstein's general relativity isn't concerned with particles, but rather the curvature of space-time, and you don't average over all the possible histories of a particle, but rather over all possible space-time geometries. That's not a full sentence, and it cuts off there. That's awkward. That's a goofy quote. All right. So when you do this, all the dimensions don't matter. The only dimension that does matter is one dimension. That's where the strings came out of. If you try to do it across a 3-dimensional or a 4-dimensional platform, it adds far too many variables. So what they've done with this is they've limited it down to a single dimension, and that's where that one-dimensional string comes from, if that makes sense.
Okay,
Yeah.
so these one-dimensional strings do exist in other dimensions, but we don't do the mathematics in those other dimensions because it's unnecessarily complex.
Yeah.
Okay.
That's the answer I'm going to go with.
That's kind of what it sounds like from that quote that
that I botched.
You read there.
No.
Yeah.
All right. The ending of this article provides a look into the future of string theory. So string theory offers a path to quantum gravity, and if we make the judicious choices of the math works out this way, always fun to say that, we can get both general relativity and the standard model out of it. It's the only idea to date that gives us this, and that's why it's so hotly pursued. So what that's saying is it ties in general relativity, which has been proven through numerous things, including in 2016, 2 neutron stars collided and caused gravitational waves, which are just kind of like water waves or light waves, just with gravity. Okay. But no matter whether you tout string theory's successes or failures, or how you feel about its lack of verifiable predictions, it will no doubt remain one of the most active areas of theoretical physics research, and at the core of a great many physicists' dreams of an ultimate theory. Some more evidence for string theory. It has been largely lacking, but in 1996, Andrew Strominger, then at the Institute of Theoretical Physics in Santa Barbara, and Kumran Vafa of Harvard, simulated a black hole with an excessive amount of disorder or entropy. Such a black hole had been simulated 2 decades earlier by Jacob Bekenstein and Stephen Hawking. Nobody at the time could figure out why a black hole might harbor so much entropy. This black hole was created unlike previous black holes, instead relying on string theory to simulate it, providing a link between the complex string theory and the fundamental force of gravity that drives black holes. Although this provided some evidence, it is still difficult to prove string theory as a theory of everything, as you mentioned before. So just to recap, a theory of everything is trying to put the 4 fundamental forces together into one force, or one way to understand all 4 forces. Basically, they want to find the backbone to all those forces.
Well, it's the force, right?
Yeah.
It's what surrounds us and binds us and penetrates us.
You just had to say that word, didn't you?
That's the quote. It's not dirty.
Is that Star Wars? Yeah, I thought so.
Okay, blame George Lucas' crappy dialogue, not me.
I hate sand. Oh, nope. Man. All right. So evidence for these scientific theories, I talked about the gravitational waves and the colliding of two neutron stars, which are super heavy, and then when they collide, they create even heavier material. It's good news for fans of general relativity and the theory of space-time, which is that like space-time could do.
Oh, space-time's just that like time is or our universe is kind of a four-dimensional block.
Yeah.
I believe.
Yeah.
It's the B theory,
Yep.
right?
Well, yeah.
Okay.
And then we perceive it in the A theory, really.
Right. Well, yeah.
Which we could do another one on theories of time too.
Oh yeah,
it just pulls up. String theory pulls out so much stuff from other theories. It's really weird to start with it, but it might provide some good episodes for the future if we start out with this.
Right. Yeah.
So, as I've said, a theory of everything could be a different topic all on its own, but it's important to our discussion on string theory. As described before, theory of everything ties the four fundamental forces together. Two leading theories are the string theory and the quantum loop gravity, although quantum loop gravity is a topic for another day, just like half of the stuff we've talked about. So why do we want to unify those forces? It's been observed over the years that certain unrelated topics within physics, as I've said, like light waves and gravity waves and water waves, but also like pendulums oscillate just the same as a spring bounces back and forth. If you were to graph the graph on the timeline, it shows a sine curve, and that sine curve is very similar between those. Although you can explain that one with classical physics, just the way springs and pendulums work, but it shows that gravity acts the same with different topics.
Right.
Yeah.
It's a uniform experience throughout our world.
Yep. So a theory of everything could be the breakthrough in science to help us understand physics from subatomic all the way up to a multiverse. Maybe not. String theory hasn't made it all the way there. It's having those difficulties reaching those 3 to 4 dimensions, and that's where a lot of people are working on that issue. Hopefully I got the basics out of the way. You got any more questions for me, Scott?
Yeah. So first of all, just helpful reference. So you say that string theory involves pulling in a lot of different other, topics.
Yeah.
So if somebody's listening and they're like, okay, this string theory stuff really interests me. What are some topics that they ought to do research on? Like what's a list of some good topics to help flesh out their understanding?
So you'll want to try to understand some relativity, both general and specific, I believe. Special, excuse me. You'll want to understand some of that, and you'll also want to understand some of the other theories like quantum loop gravity. Basically, just get a physics degree. Not really. You don't need a physics degree to understand it, but classes at a college would help in that area.
Right.
I'm trying to think of what else. What else did I mention? Relativity.
So,
understanding of those four forces that I just briefly discussed. That's very important. Also, quantum field theory, because it's a underlining topic behind string theory.
Right.
So yeah.
Is that okay? So those topics are good to know if you want to dive deeper into string theory.
Definitely.
So something I wanted to talk about. So you said earlier that the evidence for other scientific theories like general relativity, like the gravitational waves you were talking about. So that provided evidence for general relativity in like space-time.
Yep.
And you said that those were requirements for theory of everything. So my question is, because philosophically, I'm averse to this idea of space-time because I think it's got issues, philosophically. So if that's the case, would philosophical arguments against space-time and Einstein's understanding of relativity just rule out right away string theory? Because it would undercut those two.
It's possible if you're looking at space-time as stating that like an A theory of time couldn't exist, but an A theory and B theory can like coexist, can't they?
No, because they're about the way reality is. They would both, I guess, empirically they would appear the same.
Yeah.
But metaphysically, they're quite
very different.
Yeah. Sorry about talking about all these time theories. That's something we'll get into in later episodes. That's something I want to talk about. It's one of my favorite areas of philosophy to talk about is the theories of time. So we'll definitely get into those.
Yes, it's definitely interesting. I would say that there's evidence for some form of space-time, but I'm not going to say it's necessarily a 4D block. Mm-hmm. Basically, when you travel or when you approach the speed of light, let's say that the speed of light is the limit that you can travel.
That you can go, right.
As you approach that, your perception of time changes, and that's really what the relativity and space-time have to do with. So it's not necessarily the 4D block that philosophers may argue for or against. It's just it's a relative thing, or it's a part of relativity, because our relative perception, or not necessarily perception, but the amount of time that we spend depends directly on like how fast we are traveling through space. Is how I've understood it.
Yeah, and I guess when I think about it, because empirically the two theories of time are similar, or they would appear the same. There really couldn't be empirical evidence towards one or the other. I guess it's probably not as big an issue as I initially thought. So another question I had is, you said that this is really popular among physicists today, the string theory.
Yeah.
What's the other? Okay, so there's quantum loop gravity theory.
Yep.
So do people think the classical physics approach is just insufficient then, and that's why they're looking for these? Or are there people that still say, no, classical physics got it right, you guys are stupid for thinking string theory is anything big? Or how does classical physics fit into the string theory idea?
So do you know how quantum mechanics works at all?
Yeah.
Okay. So when energy is put into an atom, electrons will jump from one level to another.
Right.
Correct?
Yep.
So that at that level, and that has been observed, and you can observe it by introducing energy to atoms and then checking out how light refracts with those atoms. And so basically, once you get down to that subatomic level, then regular physics classical physics breaks down, and you get into quantum physics. So what they're doing is they're trying to break it down even further into string theory or loop quantum gravity, or any other theory that someone may think of to describe what's happening underneath the atomic level. They're trying to break that down even further.
So basically, they would say classical physics is really good up until the subatomic level, and in order to explain the subatomic level, we need things like string theory.
Yeah, they want to go. They want to go deeper to try and explain why quantum mechanics works the way it does.
Oh, okay. So string theory tries to explain.
Well, it tries to explain everything, really.
Right,
is the deal,
right. But that's a fundamental part of it. Then.
Yeah, sure.
Okay. Oh, okay. That actually makes a lot more sense.
Yeah.
Now. So cool. Yeah, and then. So then, wouldn't isn't relativity like opposed to quantum mechanics? Quantum mechanics.
Oh man, you're leading me down a road. Yeah, I still need to do a lot of research on relativity to fully understand it.
Sure. Well, nobody understands general relativity.
Yeah.
I'm convinced.
Yeah. Relativity and quantum mechanics. Let's see what Google pulls up.
Well, okay, I remember I always read that those two both cannot be true.
Yeah.
But they both seem to be true.
Yeah. That's probably something that I'll have to do some more research on and get back to you. We may revisit this quite a few times.
Honestly, we should really get a guest on.
That fully understands it,
studies this. Yeah,
yeah.
That might be a good idea.
Definitely.
We'll probably I'll put some feelers out and see what we can
Sweet.
get.
That'd be cool
for that. So
yeah.
So yeah, those are my questions.
So what I'm getting here, and this is an article from The Guardian in 2015. They say relativity and quantum mechanics are fundamentally different theories that have different formulations. It is not just a matter of scientific terminology. It is a clash of genuinely incompatible descriptions of reality.
Right. Yeah. That's what I remember. And that's funny because that's the two pillars of physics today.
Yeah.
Basically can't both be true.
Yeah. Well,
so,
it's hard to describe. So if they're really going for support of relativity, then they may be looking for an excuse to get out of quantum mechanics. And by describing things using string theory, they could escape quantum mechanics and describe it in a different way.
Okay. So you could say if string theory is the case, then quantum mechanics isn't really quantum mechanics. It's just how strings behave when they're really small.
Yeah, that's one possibility.
Right.
Yeah.
Right. It's just so there's nothing different about it. It's just like it's not a different. I don't know what you want to say.
A different way of looking at something we observe to be quantum mechanics. So if it did turn out to be a bunch of one-dimensional strings vibrating at a certain frequency, that then it could be perceived as quantum mechanics as that atom jumping to an outer level and producing a higher frequency of light wave. Does that make sense?
Yeah, I think so. Yeah. Okay. Wow. I actually do. I feel like I understand string theory way more.
Cool.
It's not just a floaty term for me anymore.
Yeah.
All right. So that's. I guess. Do you have anything else that you were gonna mention?
Not without making my brain explode at this point.
Sounds good. I imagine a lot of people are in that boat. Same here.
I feel you. Let's remind everyone that the giveaway is still going on. You got some good chances of winning a Amazon Echo.
Really good chances.
Yeah, really good chances.
So make those chances worse.
Yeah. And then, again, this was a suggestion in our suggestions box. So if you want to hit us up, go to thebestwaytoexplainit.com/suggestions, and we will try and work you in.
Yeah, we have a bunch coming up. We've got a bunch of good shows. Really glad to keep making them. You guys are awesome, and I don't know. I'm having a blast doing it, and so hopefully you guys are too. And stick around and share the show with a friend that might find this interesting, or even if they don't, just throw it on the car and force them to listen to it, like I did to my sister. So,
there you go.
It's up to you. So
that's the way to do it.
Yeah. So that's probably it then. Yeah. So we will talk to you when we talk to you again.
Get learning.